Good morning, everybody. Welcome back to Abstract Algebra. The plan for today is we are going to finally finish this packet. Oh shoot, I just made a terrible mistake. I just realized I didn't put the next packet at the door like I was supposed to. We'll cross that bridge when we come to it. But today we're going to finish proving the fundamental theorem of cyclic groups and then finally be ready to jump into chapter 5, which is going to be focused on permutation groups, which is another kind of example of a group type that we'll be using throughout the semester. As far as office hours go, I've got my normal ones this afternoon from 2 to 3, tomorrow morning from 10 to 11:30, and tomorrow afternoon from 1:30 to 2:30, Wednesday morning from 10 to go right before class, and Wednesday afternoon from 2 to 3. As far as homework goes, homework 4 is up. It will be due Friday. So yeah, I'm still not finished grading homework 2, and I apologize for that, but poor decision making has led to a semester where I've had the most grading out of all the semesters I've ever taught. So, I'm going to try and get that homework 2 graded the next few days, and then homework 3 will hopefully be graded next weekend, but we'll see how that goes. Yeah, any questions or comments before we get started for today? How can you tell if a clock is hungry? You can tell if a clock is hungry because if so, it will go back 4 seconds. Okay, so last time we had talked about the fundamental theorem of cyclic groups, which says that if G is a cyclic group generated by A, then any subgroup of G has to be cyclic. That if G has order n, meaning A is order n, then the order of any subgroup of G has to be a factor of n. So the order of any subgroup has to divide the order of the group if it's a finite cyclic group. And finally, we said that for every divisor k of n, G has to have exactly one subgroup of order k. And that subgroup is just going to be the group generated by A to the n over k. So basically what this theorem then told us, we looked at an example with Z mod 28Z last time, and this gives us a way to tell, given any cyclic group of order n, we can say exactly what all of its subgroups are going to look like. And we also had this theorem from last week that says if A is order n, the order of A to the k has to be n over the GCD of n and k. And I included that up here because we are going to use this several times in finishing our proof of the fundamental theorem. So we kind of got halfway through proving part 1 of the fundamental theorem last time. So I'm going to kind of paraphrase a little bit what we did to get to the point where we currently are in part 1. So our proof of part 1 looks something like, so part 1 is proving any subgroup H of G has to be cyclic. So we're going to let H be a subgroup of G. And then we show if H just consists of the identity element, then it's generated by the identity element and has to be cyclic. So we assumed H is not just the identity element. And last time we showed that if H is not just the identity, then H has at least one element of the form A to the k, where k is positive. That's something we showed last time, basically saying if H contains more than the identity, then we have to have A to the k for some non-zero k, and if that k is negative, then we just take the inverse of it, and we'll get some positive A to positive k in H. So then what we did was we let M be the smallest positive integer such that A to the M is an element in H. So the smallest positive power of A that is actually contained in H. If A itself is an H, then M is 1. Otherwise, M is going to be something greater than 1. And then we said clearly that the group generated by A to the M has to be contained in H by closure. And then we use the division algorithm to say for any B, an element in H, B has to be of the form A to the K because everything in our group is of the form A to the K. And we said for any element B in H of the form A to the K, B has to be equal to A to the MQ plus R for some R, satisfying that R has to be between 0 and M. And then where we had left off last time was we showed that A to the R has to be an element in H. And that's kind of where we left off last time. So we showed that A to the R has to be contained in H. We know that R is strictly smaller than M, and M is the smallest positive integer such that A to the M is in H. What does that tell us has to be true about R? If A to the R is in H, R is strictly less than M, and M is the smallest positive integer with A to the M in H. Okay?
It can't be a positive integer?
R can't be a positive integer, and so therefore, if R is an integer that is not positive and satisfies this inequality, what does R have to be?
Negative?
Not negative.
0.
R has to be 0. Because we said R has to be greater than or equal to 0. From what you pointed out, Gabe, R can't be positive, so therefore it has to straight up be 0. So since A to the R is in H, R is strictly smaller than M and greater than or equal to 0, and since M is the smallest positive integer with A to the M and H, thus R equals 0. Because otherwise, if R was anything greater than 0, that would contradict M being the smallest positive integer with A to the M and H, because we know that R has to be strictly smaller than M. Thus, R equals 0. So that tells us that our B, which is of the form A to the K, has to just be A to the MQ plus 0, which is the same as taking A to the M raised to the Q power, and that has to therefore be an element in the group generated by A to the M. And that's just since we showed that our arbitrary element in H has to be some power of A to the M, and if it's a power of A to the M, it has to be in the group generated by A to the M. Any questions about why that is? So we've shown now that any arbitrary element in H has to be contained in the group generated by A to the M, since every element in H must be in the group generated by A to the M, we can say that H is a subset of the group generated by A to the M. Or not even a subset, we can say H is a subgroup of the group generated by A to the M. Since everything in H has to be in the group generated by A to the M, we just showed. But since everything in the group generated by A to the M is contained in H, and everything in H is contained in the group generated by A to the M, what has to be the relationship between H and the group generated by A to the M? If each is contained in the other. They have to be equal. Since group generated by A to the M is a subgroup of H as well, we can conclude H is equal to the group generated by A to the M, hence H is cyclic. Awesome possum, lemon blossom. We just showed that if you start with an arbitrary subgroup, H of G, under the assumption that G is a cyclic group, we showed H has to be cyclic as well, and therefore, as any subgroup of a cyclic group is cyclic. We have proved number 1. Bit of a complicated proof. Definitely relies heavily on this being able to use the division algorithm to show A to the K has to be some power of A to the M. And relies definitely on letting M be the smallest positive integer with A to the M and H. Questions and or comments? All right, and that was just the first third of our proof. We still have parts 2 and 3 to go. Fortunately, parts 2 and 3, not as bad. So now, let's prove number 2. So part 2 said that if G has order n, then the order of any subgroup of G has to be a factor of n. So now, we're going to assume, we're going to suppose that the order of G, which by definition must be the order of its generator, is equal to n. And we're going to show that H is and we're going to suppose that H is a subgroup of G. So in other words, we're going to suppose we have this finite cyclic group and H, some subgroup of it. We need to show that the order of H has to be a divisor of n, the order of the group. Here's the cool thing. This would actually be really long and tedious and hard to prove if it wasn't for the fact that we already showed H has to be cyclic in part 1. So since we proved in part 1 that any subgroup of a cyclic group is cyclic, we can just straight up use that here to say, oh, we have a subgroup of a cyclic group, boom, it's cyclic. So then we can say by part 1, we know that H is going to be cyclic, and in fact, it's going to be generated by A to the M, where M is the smallest positive integer such that A to the M is an element. Basically, using our work from part 1, we can immediately say, oh, we have a subgroup of G. It has to be generated by the smallest positive power of A that'll get it inside of H. That's something we proved as part of our work in proving number 1 here. So then, that tells us right away that the order of H, the number of elements in H, has to be, well, it's going to, by definition, be the order of the group generated by A to the M, which, as we've seen, is just the order of A to the M. The smallest power we need to take A to the M to get the identity. But what's the order of A to the M? You can use this theorem. Right. It's going to be n divided by the GCD of n and n to n. N and n's. So the order of A is n, so the order of A to the M is just going to be n divided by the GCD of m and n. And what do we know about this number? N divided by the GCD of m and n. We're trying to show that H, the order of H divides n. In other words, that n is a multiple of the order of H. Do we know that this thing, or do we know if n is a multiple of this thing?
Well, we can multiply it by the GCD of n and n, and we get
N. So,
Bingo. Yeah, that tells us then that the GCD of M and N multiplied by the order of H is going to give us N. So the order of H must divide N, which is the order. And we are done with part 2. Because we've shown that the order of H has to be a divisor of the order of the overall. Like I said last time, we've only proven this so far for finite cyclic groups. It is going to be true that this property holds true for finite groups in general, that the order of any subgroup has to divide the order of the group at large. But we haven't proven it in all generality yet. That's something we'll do in a few weeks from now. Actually, not that too many weeks until we get to Lagrange. Yes, Elaine?
I'm so tired of Lagrange.
You haven't even seen Lagrange's theorem yet.
We're in math econ, is all you do, but.
Well, that's Lagrange multipliers. That's different. We're not doing any of the Lagrange stuff you do in econ.
God bless. Yeah, we're tired.
Let's say, econ you do something called Lagrange multipliers. I think it's the same Lagrange, but it's completely different sort of thing we're going to be doing.
Great. Same guy.
How many math guys named Lagrange are there?
Greater than or equal to 1. Not even a joke. That's just that's just a fact. It's greater than or equal to 1. I don't know. Now I'll go look up after class and report back to you for next time. Okay, so we've proven parts 1 and 2. Now we just need to prove part 3. So for part 3, we're kind of being asked to show 2 different things. Part 3 says, for every divisor k of n, G has exactly one subgroup of order k, namely group generated by a to the n over k. So we need to actually prove 2 different things here. We first need to show that the group generated by a to the n over k is a subgroup of order k, so it's sort of an existence proof. We also need to show uniqueness and show that any other subgroup of order k has to be equal to this thing. So sort of an existence and uniqueness proof that we'll be doing here. So we're going to start off by, we're going to let k be any positive divisor of n. We need to specify we technically need to specify positive divisor because technically, otherwise, we'll have to ask questions like, what subgroup of Z mod 6Z has order -3? What does it mean for your group to have -3 elements in it? It means nonsense. Yes, it means pull out your hair. So we only really care about positive divisors of n because those are the only ones that it makes sense to have subgroups of that order. All right, so we're going to let k be any positive divisor of n. And first thing we're going to do is we're first going to show that a to the n over k does indeed have order k. So first piece, we're going to prove existence that a to the n over k is in fact a subgroup of order n over k. And then after we do that, we'll prove there can't be any others. So, well, this is actually pretty quick to do because if we take the order of a to the n over k, of the group generated by a to the n over k, that's just so happens, it's going to be the order of the element a to the n over k. In other words, the smallest integer power to which we can take this thing and get the identity element. Well, we can use our theorem there to say this is just going to be n divided by the GCD of n in n over k. What's going to be the GCD of n in n over k? Keeping in mind n over k is already a factor of n. Right?
Over K.
Yeah, the GCD of n and n over k is just going to be n over k. And that's because n over k is already a factor of n. So the GCD of n and any factor of n is automatically going to just be that factor of n. In this case, n over k. So the order of the group generated by a to the n over k is going to be n over k, which Megan is going to be a-OK. So there we go. We've shown that the group generated by a to the n over k is in fact a subgroup of order k. Now we just need to show there can be no others. And so next thing we're going to do is to prove uniqueness. So first of all, we're going to let H be a subgroup of G such that the order of H is equal to K. And our goal is going to be, if we take an arbitrary subgroup of order K, we need to show that it has to be equal to the group generated by a to the n over k. Well, here, I'm going to do something a little bit cheaty. It's not actually cheating. But I'm going to just use our result from part 1, the same one we cited in part 2, and say, hey, H is a subgroup of G, boom. We know it has to be generated by a to the m, where m is the smallest power of a that's in H. So by our proof of number 1, we know H is going to be generated by a to the m, where m is the smallest positive power such that a to the m is in H. So again, just kind of using this thing we proved as part of our proof of number 1. Well then, by number 2, we know in number 2, let's put it this way, we know n over m, which is going to be the order of a to the m, divides n. Hence, m divides n. So basically, we know that this power of a is going to be a factor of n. And that's going to be important because then we can say that our k, which is the order of H, which is going to have to be the order of a to the m, can again use this theorem and say that's just going to be n over the GCD of n and m. But if m is a factor of n, what's the GCD of n and m going to be if m is a factor of n? It's just going to be m. It's going to come out to n over m. Since k is equal to n over m, what can we say has to be true about m? We do a little cross-multiplying switcheroo action.
N over K.
M's going to have to be n over k. Hence h, which we said is generated by a to the m, is in fact going to be generated by a to the n over k. So in other words, the only possible subgroup of G with order k has to be this group generated by a to the n over k. There we go. Fundamental theorem of cyclic groups. This theorem, again, tells us is a great, just like we did last time, you give me any number, please don't make it too big. We can use this theorem to say exactly what all the subgroups are of that cyclic, of any cyclic group of that order. Just like we did with 28 last time. It's just find all the divisors of the order of your cyclic group. So 28, find all the divisors of 28. There's going to be a unique subgroup of order each of those divisors. And that's going to give us all the subgroups of your group. So in Z mod 28Z, for instance, we found the divisors of 28 were 1, 28, 4, 7, 2, and 14. We were able to find a unique subgroup of each of those orders. And we just took our generator to the power of n over k each time. Questions or comments? Y'all sick of these long, drawn-out theorem proofs? Let's do some more examples then. Okay, forgot to put this out in front of the room. I blame Dr. Murphy for distracting me. So I'm going to go ahead and pass out another worksheet. Thank you. So now we're finally ready for chapter 5. It's going to be about a new type of group called a permutation group. So permutation groups are just going to be a class of groups that are made up where the elements in our group are all going to be functions. So we've already seen one example of a type of group whose elements are actually functions, or a type of transformation. Which group have we seen so far where all of the group elements are actually somehow transformations of some object? Okay.
The dihedral?
Yeah, the dihedral group is made up of basically functions that say take a thing and rotate or reflect, or some combination thereof in a particular way. Permutation groups are actually going to be a generalization of dihedral groups, in that permutation groups are elements are just going to be functions that go from a set to itself, and that have these properties of being one-to-one and onto. So, given any set A, we're going to say that a permutation of A is a function f that goes from A to A that is both one-to-one and onto. So, a bit of notation time. When we say a function f that goes from A to A, what we really mean is this A is going to be the domain of our function f. So we want the domain of our function f to be equal to A. What's the domain of a function? Anybody remember from a calc course once upon a time? What does it mean to say that the domain of a function f is just going to be the set A? Wrong?
It's the set of all things you can put into a function.
Yeah, it's just a set of all values that you can plug into a function. So here, when we say the domain of f is equal to A, what we mean is our set of inputs is going to equal just the set A. So we want to be able to plug in any value in a into the function f. And this a is going to have a special name. You might be thinking, oh, Dr. Gersel, that's going to be the range. You would be thinking wrong. It's called the codomain. So let's probably write out these words, codomain and domain. The codomain of our function f is just going to be the set of all potential outputs. So if, for instance, we were to look at the function f going from the real numbers to the real numbers, if we were to take f of x equal to x squared, the codomain of the function f is just going to be the real numbers. The domain is also going to be the set of all real numbers, because we can plug in any real number into f of x and get an output that makes sense. Is it the case that every real number is going to be an output of this function? Meaning, if I were to take something like x equals -5, is that going to be an output to this function? See lots of head shaking. Anyone going to be brave enough to raise their hand and defend their answer? Rowan.
No.
Thank you, Rowan. Yes. Turns out in this case, the codomain of this function may be all real numbers, because that's the second r. But in this case, not all real numbers are actually going to be outputs, because you can only get 0 and positive numbers as outputs to this function, assuming you're just plugging in real numbers. If we're allowed to plug in complex numbers like I, then we can get negative outputs. But if all that we're plugging in is real numbers, our outputs are only going to be positive real numbers as well as 0. So even though not all real numbers will actually be outputs. So the codomain is just going to be the set A again in all the examples that we look at. But the set of all actual outputs, the range in other words, may be different from the set A. You could, any questions or comments so far? Dr. Gersel, you used the words one-to-one and onto. What do those mean? Good question. So when we talk about permutations, you may have noticed I said it's a function that goes from a set to itself that is one-to-one and onto. I'm guessing a lot of you have probably seen these words before. Now, those of you who took discrete with me in the spring certainly did. But if you haven't, what it means for a function f from a to be one-to-one, and if you write, and I'm lazy, so when I write out 1-to-1, I'll just put 1-1. That means 1-to-1. Function f is 1-to-1 if whenever f of a is equal to f of b, it must be the case that a is equal to b. i.e., no two inputs match the same output. So if you were to look at a function like f of x equals x squared, would that be an example of a one-to-one function? meaning is it impossible to have two different inputs give the same output? Or are there two outputs to this function that would produce the same output?
Not 1 to 1 plus 2 and negative 2 both.
Yeah, we can find two inputs, 2 and negative 2, for instance. So really any a and negative a would work. We could say that since f of 2 is equal to f of negative 2, but 2 and negative 2 themselves are not equal, f of x is not 1 to 1. Whereas if we were to look at a function like, I don't know, what did I end up putting in the packet? G of x equal to 2x. I claim this would be an example of a 1-to-1 function. Since if g of x1 equals g of x2, i.e. if 2x1 is equal to 2x2, we must have that x1 and x2 would have to be equal. In other words, for g of x, it's impossible to have two different inputs map to the same thing. Because if you have two things that map to, if you have an x1 and x2 that map to the same thing, then x1 and x2 had to be equal to begin with. Whereas for our original f of x, we could have two different things that map to the same elements, 2 and negative 2 as an example. So that's enough to make f of x not 1 to 1, but g of x is going to be 1 to 1. I should have given you more room on the front page. My apologies. Any questions about what 1 to 1 means? So for onto, you notice how we said the codomain, the set A is going to be the set of all potential outputs, but you could have things that don't get mapped to. If the codomain and the set of all actual outputs match up with each other, then we call our function onto. So let's write that down. A function from A to A is onto if given any element in A has to be equal to f of b for some b in element in A. Which is a fancy way of saying, or which is a less fancy way of saying the codomain of our function f is going to be equal to the range of function f. So if we were to look at our same example, f of x equals x squared and g of x equals 2x, given any real number, and here these are both going to be functions from the reals to the reals. If we look at the function f of x that goes from the reals to the reals, f of x equals x squared, is that going to be onto? Meaning, given any real number, can we find some other real number that, when squared, will give the original? Or, is there a real number that is not equal to any other real number squared?
It's not going to be onto because of the negative numbers.
Give me an example.
Negative 2.
Negative 2, okay. So not onto, since, for instance, negative 2 is not equal to f of x for all elements x in the reals. There's no real number that will map to negative 2 under the function x squared. Therefore, this function cannot possibly be onto. Whereas g of x, I claim, is onto since given any, let's say, any real number A is I can always find some elements in the real numbers such that G of that element will give me A. And what would be an example of a real number that's going to map to A if our G of X is 2X? What's going to be something that if we were to double it would give us back our arbitrary A? Yeah, A over 2. Given any real number, given any real number, it's going to be equal to G of exactly half of that number. And so that then will tell us that G of X is onto, because given any real number, we can always find another real number that will map to it under our function.
For an example of something that's not, or that is one-to-one but not onto.
Ooh, that is one-to-one but is not onto. Indeed. You said one-to-one but not onto? It's one-to-one because e to the A equals e to the B if and only if A equals B for real numbers. But it's not onto because e to the x, just like x squared, will never give you a negative number. All right, and while we're doing it, let's see, what's the other one? That's one-to-one but not onto. Let's do onto but not one-to-one. Another example of, no, that would be neither. Never mind. Let's see. So this one would be an example of one-to-one not onto. Let's see, I want something that's onto, but not one-to-one. Do I have a good example that's not a piecewise function, not the top of my head? Yeah?
X sine of X.
Yeah, that is certainly onto. That is certainly, that works. It does not obviously work. I'll put it that way. How about this? There. This will be an example of a function that is very much onto. It takes on every real number value. But it's very much not one-to-one. Because there's infinitely many values, infinitely many inputs, for instance, that will give you 0 as an output. Okay, my example really wasn't any better than yours. I think x sine of x ends up, what's it, something like that. It's kind of like some wibbly wobbly that kind of keeps going back and forth as x increases. So a permutation is a function that does both of these things. It is one-to-one and onto. So for instance, g of x equals 2x as a function from the reals to the reals would be one-to-one and onto. G of x equals f of x equals x squared is very much neither of those two things, and so it is going to fail to be a permutation. You got 5 minutes, 3 functions at the bottom of the page. I want you to tell me which ones are permutations and which ones are not. Give you 2 kind of standard examples and 1 twisty example. So for one-to-one, you need two things, no two things can map to the same output. And for onto, every possible output is an actual output. If you feel comfortable doing so, you are welcome to share your thoughts with your neighbors on this.
I think the first one.
This is yes.
That's just like.
I
put no.
Onto every possible output.
We'll just suppose
Kind of like limited.
like letter A. Okay.
Yeah.
Like the same, like none of those seats are in the, none of those exist. It's like this is a set of all the seats that they're currently in.
Gotcha.
I said no because it's not gonna
Right.
be
Or wait,
So it
yeah, that
would
cube
be
plus one.
onto because if I'm thinking about like
Interesting.
all
I
the
don't think it's that
possible
hard to watch.
outputs, I would say like
basically
every
able to
set,
find
like
the
every
place.
combination.
Yeah,
We're
but
going
it's
to
just
get
like-
one.
Yeah.
Because there's
What is, like,
I said the same.
And on number two, I was mean and I didn't tell you exactly what the set is.
Yeah.
Let's say the set for number two is the set of all seats that are currently occupied by a student. That's our set. That's our set A.
Yeah.
Well, Dr. Ursel.
Because we're.
Dr. Ursel. Wouldn't that be the codomain?
That would be
Domain is
the
the
domain
student.
and codomain in this case. The set of all seats currently being occupied by a student.
Wouldn't the domain be the students and the codomain be the chairs they're sitting on?
Does it allow to map to chairs that are not being sat on?
So the idea of the function I had in my mind is f of your seat is after the musical chairs arrangement, the seat that you end up in. So f of Rowan's original seat equals Rowan's new seat. I should have thought this through a lot more. That's a,
So it's gonna work out.
Like number all of the seats. It depends on whether it's true.
Yeah. that's right.
You said we're not.
We're not, the ones you said that.
Either I didn't.
Oh, okay. So it's only those chairs, not
Yeah.
those people.
What are you saying about numbering the seats?
Like if you numbered all of the seats, then you could like do seat one, seat two, seat three, yeah. Then it would be like F of like my name, using just right, W name, so I'm gonna be in my seat 12. So it's gonna be like F of 5 is 12.
Interesting.
Right, but so for every single number, you're just gonna map it to a number, it's just gonna be.
Yeah.
What if someone was already sitting in the
It
seat?
doesn't matter, so.
It would be fine.
Wait,
It would be like F of 12 equals
Wouldn't
12,
an
but
X
no one
have
else
to be a
would be
chair?
Okay,
right.
yeah, that makes sense.
And all, since we're not using any of the new seats, or any of the empty seats, we don't have to worry about the seats.
Okay.
You want the-
The other thing about it is it isn't the seats, it's just our order.
Yeah.
Yeah, does that make you feel better?
No.
Right.
This is just
Moving around.
X isn't
Yeah.
even
Who's
an
sitting,
A.
yeah.
well, true, but we're not mapping elements of this set to anything. We're just saying you take
One minus
the A is this X gets associated with the seat. And so when we say X's original chair, that's something that is an element in A, even though X itself is not.
Yes, sir.
Elaine, you are in this set, but you are not in that set.
Yeah.
Your desk, however, is in the set A, that is going to be the domain and codomain of this function. Hey, you know what? Think about it, and we'll talk about it on Wednesday. So on Wednesday, we'll talk briefly through each of these examples, and then we'll start talking about what is the actual group structure that's going to go on here when we talk about a permutation group. It's going to be very similar to the permutations we saw back when looking at the Dihedral group. Good day, everybody.
Sometimes.